we first do the design entry. Now I know that my team is to develop that face recognition hardware. Okay, the 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 sensors will give me some data, and I have to now design the hardware which would do the calculations to ensure that face recognition happens accurately. So I do the design entry, I make it an RTL or something like that. After the design entry, I synthesize it. I say that, okay, I wanted adder there, I wanted a multiplier here, I wanted a comparator here, and so on, and I synthesize it. I make those connections. And then I simulate it, saying thereby that the adder and the multiplier and the connectivity of them is working fine. It is at this stage, when you are simulating, and if the simulations come fine, it is at this stage that you may also want to emulate. That is where the FPGA or other emulation systems would come in. Okay. And then you enter into the stage of physical design and layout. This is hardcore implementation. And once that implementation is done, you will simply do a design verification that whatever chip I have now designed, I have now implemented, that is in line with the design specifications that I had. Okay. And then what we would do is we call it as a tape out. Then we tape out our chip and send the design to the foundry. In the foundry, yes, Raghav?
So the design verification step you have put it at the very end, but design verification, as I can remember, it comes after synthesis also, and like after this,
yes,
at various stages. So what kind of design verification are you like focusing on here and the step? Because
so this is so the design verification that I have put on this slide over here at the bottom of the design implementation stage is exhaustive. It includes simulation-based verification, includes stages like DRC, LVS, ERC checks, everything. Package verification, everything is done in this stage. Only after everything is fine, you send something for mask making.
Okay, and so like we are also including the formal verification and those kind of things.
Yeah, we will look at that in the next slide because that is too much detail. So
okay, sir.
Over here, I've just put the entire design implementation phase into 5 stages. So on the next slide, we will look at all those detailed, that these 5 stages are actually a mix of 20 other activities, and each of those 20 activities is a different job profile. We will look at that in the next slide.
Yes, sure, sir.
Okay.
Sir,
Rajneesh, you had a question?
Yes, sir. Sir, in this design implementation, sir, this like logic partitioning and planning is present in this physical design also, no, sir? This.
Yeah. The floor plan placement, everything. We will talk about in the next slide. Don't worry. Design implementation, we will go into much more details in the next slide.
Sir, these two are different, no? This design analysis, partitioning, and plan and.
Yes, they are very different. Partitioning that I talked about in design analysis was which team where will do which kind of designing.
Okay.
That was the overall partitioning of the project.
Okay.
Sir?
Yes.
Yeah, so I don't understand what's the difference between synthesis and physical design and layout.
We will see. In the next slide, we will see, Meher.
Because, I realize this might be a little different, but from what we studied about FPGA, like when you're doing synthesis, you are doing a mapping and routing. I mean, all that placement and all that, isn't that a part of your layout itself?
So we will see that in the next slide, Meher. Just wait a little.
Sure.
Okay. So keep this question alive in yourself. We will see that in the next slide. Let me just give you a complete top level overview first, then we'll go into the detail. Okay. So once we are sure that the chip that we have designed, the layout that we have designed, everything is really good to go, we send it to the foundry. The foundry first sends it to the mask shop where masks are made. And once the masks are available, you start to do the wafer fabrication. Now, depending on a technology, there could be 39 masks, there could be 28 masks, there could be 47 masks, or there would be 60 masks that a design or a wafer would need to go through to make the entire design. So it would depend on technology and the choices that you have made regarding the design. Okay. And the more the number of masks, the more the time it takes in the fabrication facility, because it is more number of times it has to sit into machines and run through it. And also higher the risk of yield loss, because every mask step, every additional step in the foundry means some yield loss at every step. So every extra step means some extra yield loss that can happen. Yes, Vaishnav.
Sir, what is this mask exactly, sir? I mean, like.
Yeah, we will come to that. So mask is like something that we will use to fabricate a design. Okay.
Okay, sir.
So when we will look at the fabrication process in probably the next class, or hopefully today, I don't know, you will get a view of what a mask is. Okay.
Okay.
So yeah, once the wafers are fabricated, they are sent for testing and characterization. So the first test that happens is wafer prototype test. What does it mean? It means that at the wafer level itself, without even cutting the wafer into dies and cutting it into chips. So you know how a wafer looks? A silicon wafer is for example, a 300 millimeter wafer means that there is this circular silicon wafer, thin piece of silicon, which is 300 millimeters wide. So 12 inches wide. The diameter is 12 inches. And on this wafer, there would be, these, I think that PPT has
So
got.
did you just say that the diameter is 12 inches?
Yeah, the wafer is 12 inches.
Isn't that quite big? I mean,
Yes, it is big. On one wafer, you can have thousands of dies that can be fabricated.
And sir, what exactly are dies?
Die is the chip that will go into your phone.
Oh, okay.
Okay. But yeah, you manufacture all of them together, so many of them together, so that the overall cost can be low.
Okay, so basically we are manufacturing many dies in the same wafer, and then those dies can be later separated.
Yes.
Just to decrease the manufacturing costs. So we are manufacturing them in bulk.
Yes.
Right.
So the first test you do is on wafer level itself. That, okay, let me see how many dies in this particular wafer are working. After that wafer prototype test, you identify the good ones, and only those good dies you package. You don't package the bad ones. After packaging, you do another testing.
So we are testing the good ones twice, effectively.
Yes. So hoga kya? So as I said, every step that you take, there could be some failures happening there. So on the wafer, you saw that, okay, out of the 1000 dies, 990 dies are working. So you say, okay, I will package these 990 dies. After packaging, out of those 990, 980 may be working. So only those 980 you will then send to the customer.
Sir, but why will something like that happen? I mean, are we using different tests in both the levels? I mean, wait prototype test and then package prototype test.
Okay.
And
let us put it like this. Have you done some painting any point of time in your life?
yeah.
So the first step you do is sketch it with pencil.
Yeah.
Then you start to put some colors into it.
Yeah.
So you suppose you have to put, you have to make a rainbow. So you have to put 7 colors next to each other.
Yes, sir.
Now I want only that particular painting to be shipped in which there is no overlap of any color.
Yeah.
So what can happen? After the first step, that is I made it with pencil. Okay, pencil mein to kuch overlap ka koi possibility nahi tha, so it is fine. There is no yield loss. After the red color, again there is no yield loss. But as soon as I put the orange color, I might end up overlapping it with red somewhere.
Okay. Okay.
So that
I get it. So like
particular
every
painting goes
stage.
for a toss.
Yeah. Yeah.
So every extra step that you do, there can be some yield loss.
Yes, sir. Yes, sir.
So when you
I get it.
package, what are you doing? You are connecting wires from the pins of the package to the pads on your die.
Okay.
There could be some error in that connection.
Mhm.
Therefore, yield loss.
Okay.
So you have to test after every step.
Got it. Got it.
Yeah. Yes, Gagandeep and Rajat.
Sir, I have question regarding the wafer. Sir, we have wafers for, making the dyes on it. But sir, for mask also, is there any wafer? And how do we make the mask? Because we have to inscribe some pattern on it.
So wait, we'll come to mask a little later. As I already mentioned, we will look at what a mask is a little later. Don't worry.
Okay.
So in wafer prototype test, is it we are just cutting each and every die and then testing it separately, whether whether the dies are working or not, or is it like we are just testing a bit a part of some that wafer? Is it like
So
that?
in a wafer prototype test, you just keep the entire wafer there. You bring probes and you put them on every die one by one.
Okay, sure.
Okay, and you test it. Now, suppose you see that there is this entire row which is not working. You will not cut the dies of that row into independent pieces. You will just discard the entire row when you are cutting the wafer.
Okay.
Sir.
Yes,
So
Raj.
what do you
Yes,
mean by
Raghav?
what do you mean by the term characterization? Is this?
Characterization essentially means what is the character of this. So characterization essentially means that, okay, I wanted to design a processor which would work at 1.2 gigahertz. Okay, but I designed it for 1.2 gigahertz, but due to some reasons, it could work only at 1.1 gigahertz on silicon. Can it happen?
Okay.
So I need to know at what speed it is working. So that is why it is called characterization. So it is the characteristic of that die that this die is working at 1.1 gigahertz and not 1.2 gigahertz.
Okay, so like I started with a certain kind of a goal in mind, but if it is like differentiating from that, I need to know that, okay, how much it is.
Even if it has met the goal, even if it has met the objective, I need to know that this is 1.2 gigahertz or 1.21 gigahertz.
Okay, okay. So like finally it is completed. Now what is like,
yes,
what kind of chip
what
it is?
is
Okay.
it?
Okay.
What is it? Finally, it is completed. Now, what is it?
Okay.
Look at it like this. So, childbirth. Huh? So you do an ultrasound, you do everything, you know that the child is developing. So I don't know, none of you have children yet, but some point of time you will have probably. So, you know, ultrasound and all those tests, you see that the child is growing well. But finally, when the child birth happens, you get to see, okay, इसकी आंखें जो हैं पापा से मिलती हैं, lips जो हैं मम्मी से मिलते हैं, and all that characterization happens.
Okay, 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 fine.
Yeah. So that is what it is. Okay, what is this? What is this die finally? It is working fine, but what is it finally? Is it operating at 1.2 gigahertz, 1.24 gigahertz, or 1.16 gigahertz? It is working fine. What at what frequency? Similarly, at what power consumption? At what leakage? At what battery life? All those things. Everything is characterizing that particular die.
Okay, okay, okay. Thank you, sir.
Okay. Shivam, you had a question?
Yes, sir. Sir, actually, I want to ask that whether the number of transistors that are to be manufactured on this dies is decided by your requirement or specifications, or is there any rule that a fixed number of transistors or will be manufactured on the particular die?
You tell me, what should it be?
Sir, it should be according to our requirement.
Yes. So it can happen. For example, someone may say that I need 1 billion transistors to be put. Now the technology team may come back and say, see, if you put 1 billion transistors, your die will become this big and the yield will be less. Instead, we recommend that you put 500 million on this chip and add another die, which is another 500 million. And together you will be able to come up with a much cheaper and a more efficient product. That may happen, but you would want to put number of devices based on what your requirements are.
Yes.
Okay.
Okay,
There could
sir.
be a technology constraint. इससे ज़्यादा डालोगे तो risk है. You can accommodate that. That's a different thing.
Yes.
Yes, Faisal.
So when we are saying that we want, our goal is 1.2 gigahertz and somehow we got 1.1 gigahertz. Now, why the customer would accept our chip now?
So you tell me, do you purchase an Intel i3 processor or not at all?
Okay.
I will sell it cheaper.
Yeah. So, but if we want 1.2 gigahertz, so we should aim a bit higher, like 1.25 or 1.3. Then we'll get
whatever.
It can be done.
Finally, what I need to do is I need to characterize and tell this is 1.1 gigahertz. I will sell it $100 cheaper.
Okay.
That I still need to do.
Okay. वो negotiation हो गया फिर.
Yes.
Okay, sir.
And something that is working at 1.4 gigahertz, I will tell the user, oh, this is very low power, and I will sell it as i7.
Yes, sir. Okay, sir.
You see? So I still need to know this information.
Okay.
How I achieve, what I achieve, that is a different thing. That is strategy, designer strategy. We are presently talking about what does the flow entail. The flow entails identifying and sorting them. So wafer test and die sort, package test and sort. If these packages are operating at this frequency, these packages at this frequency, and therefore I will sell them separately.
Yes, sir.
Okay. And then I finally ship it to the customer. Finally. Okay.
Sir, after the wafer prototype test, so here we have tested the functionality, whether our die is working properly or not, or for every row or column, whatever we say. But then, sir, will we do packaging after that only, and then move to package prototype test and then to wafer test, or would it be like wafer prototype test and then wafer test and die sort?
So see, wafer is when all the dies are together.
Yes, sir.
Packages after you have separated these dies and packaged them into their ICs. So
Yes,
after a package test, wafer test can't happen.
Yes, sir.
So in the last step, ship production units, when I say wafer test and die sort, that step is not coming after packaging. That step is coming after wafer prototype test.
Okay.
Because at times what happens is, for example, that Apple face recognition thing. You said that laser someone would make, image sensor someone would make, and the computational processor someone else would make. Something ST made, something Samsung made, something Sony made. So now you cannot package just the sensor and say, okay, this is a chip. Apple had a product in mind where all these three dies would be put together. So you're sending only the wafers and dies to the customer. You're not sending packages to the customer.
Yes.
So at times you send wafers and dies to the customer. At times you send packages. Whatever it is, you do the testing, and only after that testing you send them.
Yes. Okay.
Sir?
Okay? Yes.
Sir, in the wafer prototype test, we put the probe on the each die when it is part of wafer. We test it whether it is functionally working or not. And then in the wafer test, what kind of test we are doing on that? What is the difference between these kind of tests? Like,
so wafer prototype test and wafer test could be similar, but the last stage involves die sorting.
Okay. So like we have characterized before, now we are like putting them different categories.
Yes.
Sir, can you elaborate on die sorting again?
Yes, that okay, this die is working at 1.2 gigahertz, this die at 1.4 gigahertz, this die at 1.1. So sorting them into different bins and saying this one sell at $100 cheaper, this one sell $200 costlier, this one sell at the target price. Right.
So I mean, all the dies in the wafer do not need to be of the same type.
May not be. Yeah, may not be.
Okay. So, sir, I mean, do these steps happen in parallel? Design, characterization, and ship production units.
Depends. They could, they may not.
Okay,
It
because
depends from product to product.
Yeah.
Depends from product to product.
Yeah, because the thing is, you can do die sort right after the package prototype test. So like,
No.
I don't see why you need to do a wafer
Wait.
test.
Meher, if you've already packaged it, then you can't, then there is no longer die sort, then there is package sort.
Okay, like package sort involves what exactly?
Same thing.
I mean,
It is just that
same
you're
thing.
shipping packages instead of dies.
Okay, so I mean, then what's the so like okay, you're performing wafer prototype test and you're performing wafer test and die sort. Instead of that, you can just do wafer prototype test and follow that up with die sort. So I
You can do
mean,
that.
okay,
You
so
can do
like that additional wafer test is just like optional.
So again, it depends, if the wafer prototype test because of it depends on the fab conditions. Suppose you say that wafer prototype test was done at at TSMC, and wafer test and die sort Qualcomm would do at its own facility. So testing has to happen twice then.
Right. So it depends if it's happening at the same place or different.
Yeah. If it is Intel, it will only happen once.
Okay.
Sir?
Yes, Deepan?
Sorry to interrupt. Sir, my question is, sir, so there can be variation in the thing which we are shipping. We can ship the package, or we can ship the wafer, or we can ship the die, or because as you said that at different company, different type of tests can happen. So that means there can be different type of product which is being shipped. Is that correct assumption?
Yes. There are, for example, the RFID tags that you keep in your shirts. Those are small chips which are sent only as dies, which are shipped only as dies on strips of paper.
Okay.
So all kinds of forms and features appear in these shipping parts. So I see the hands of Vaishnav and Gagandeep also raised.
Hello, sir. I want to ask that we are doing die sorting, and then we are going to do the package sort also. So I mean, it looks like that we are doing a die sort, which might not really affect what we sell, because at the end, if I sort the packages, then I need to ship those only after categorizing. So
yeah, but if I'm shipping dies, Gagandeep, if I'm shipping dies only, then I don't need to package them, no?
Yes, sir. In that case, it would be.
Yeah. So not something that has already been packaged will not be wafer tested and die sorted. It will only be package tested and sorted. Something which is being shipped as a wafer will be wafer tested and die sorted.
So it is about what I am going to ship.
Yeah.
Hello.
Okay.
Hello.
Yes, Vaishnav.
Yes, sir. Actually, you were saying that wafer पे तो कुछ भी हो सकता है, like i3 or i7. For example, if you take an Intel, so aren't we doing something? I mean, like we would know that before. I mean, like we are supposed to make an i7 processor, but we got an i3 processor while doing wafer testing. Is it something like that, or हमको पहले ही पता है हमको i7 करना है, इसलिए in this rows we have made this i7 processor and the next rows we have made i3 processor, or is it like ये तो कुछ भी हो गया, I mean, like something has happened and due to some malfunction we have got an i3 processor or something like that?
Yeah, it could be that, no? So I gave the names of i3, i7 and i5, but let us say that have you seen that there are products which are exactly the same specification, but the frequency is lower, only frequency is lower. See, there is a difference between i3, i5 and i7. That difference is not just about speed, that difference is also about hardware. Okay, so that could be because some hardware on i5 failed and now you call it i3.
Okay, so my doubt was that actually पहले तो i3 बनता था, उसके बाद i7 आया. So have we done something unintentionally or something so that by mistake you have got an i7 processor, or during the functional and test specification?
No. It was designed to be built as an i7 only. Therefore, we designed an i7. But when i7 could not, when there were some dies which could not really give that kind of functionality, and we felt the customer will not purchase them at that price point, we said, okay, we will sell them a little cheaper.
Okay, sir. Okay. Thank you.
Okay. So let's not get into i3, i5, i7. Let me say that i7 here. Let us say it is only i7, but there are 3 different frequencies of i7 itself. And each of those i7s will sell at a slightly different price, sale point.
Okay, sir. Okay. Thank you.
Okay. Yes, Akshat.
Sir, I have a question. Like in last generation of Intel processors, something like happened in laptop that i5 is performing better than i7. So what kind of sorting issue was that? Sir, it actually happened and Intel was confused. So what kind of issue was that?
Yeah. So that is where machine learning comes into VLSI. Okay. So they defined some tests and they said that, okay, if these parameters on the particular die are positive, we will call it i5. If these additional 5 parameters are positive, we will call it i7. Okay, this was based on their understanding of the design that when these 5 additional parameters are also positive, that is when the performance will be better.
So it was not an hardware issue.
It was their understanding of how to sort.
Okay.
One way, so this is a bit confusing. They got confused. I don't know what exactly happened, but given from what he just said, they confused between i5 and i7 because there was a mix-up with the specification.
Yes, because they felt that this would be faster and it was not actually faster.
So I mean, isn't that like the job of, your design implementation and then your design characterization? I mean, if you're designing it such that, okay, it should be faster, you know that you're designing an i7, right? So
yes.
If it's showing that particular speed, then how can you sort it differently?
See, it is not just about speed, Meher. Like, it is not just about clock frequency at which you are operating. Benchmarks actually test how well you are able to use the access to the memory, for example.
Okay.
Benchmarks would also relate to how easily you are able to transition from one thread to another. Benchmarks test a lot of things. And real life use cases are also like that. You're not, just looking at clock frequency and saying my system is faster. Finally, you go with your experience, An Apple chip, an Apple iPhone chip would typically, if you look at it, operate at a lower frequency, but has a much more fluid user experience than an Intel chip-based design.
So would you say that the fault was in the test specifications? That, okay, it did not test all the cases?
So it could be anywhere. It could be in their understanding. It could be in the design implementation. They had designed it such that the memory would, they have put in more memory and they said this will actually lead to better performance. But due to more memory, what happened was the wire lengths increased, let us say, and delays increased. So, or there was a bottleneck in terms of bandwidth, due to which the information transfer that you anticipated did not really happen at the same rate.
Right.
The fault could be anywhere. I'm just saying that if they say that, okay, this was expected to be faster and it is slower, it could be simply a die sort algorithm failure also.
Okay.
It could simply be that, but it could be anywhere else previous in the chain also.
Right. Okay.
Okay. Should you move
so
forward?
how do we resolve this kind of issue then? Like,
so you go back, review your design, you debug where did the assumptions go wrong, and then you correct those assumptions, redo so you cannot really undo what has already been shipped to the customer.
Yeah.
But the next chip design that you're doing, you have more mature assumptions now, and you will therefore design it better.
So, but the problem was with the fact that, I mean, one of the possible problems that, okay, you couldn't identify one type from another because
Yeah.
It
So you
wasn't
will,
showing what you expected.
yeah.
So
So
how
you will
do we
then
make that
upgrade.
output?
Yeah. So then
Yeah.
you will upgrade your sorting algorithms, Meher.
Okay.
So the next lot that you will sort, you will have a better algorithm. So therefore, the problem will disappear after some time.
Okay.
So you retrain your algorithms then.